Yes, Shwana, am I audible to you?
Yes, ma'am.
Okay, so see, this is the relationship between the electric field and the potential. So when we are seeing the derivation, you just have two things. You are equating the work done. One work is between the charge and the potential that we are writing. And second one, which we are writing, is the formula that is force into displacement. So when you equate both of these, you get E is equal to minus dV over dr, which is the rate of change of potential. Okay, so this is very important. This basically says that electric field is directly proportional to the potential gradient. Whenever Shwana, you witness the term gradient, it should immediately come to your mind that, see, gradient means something which is changing with respect to time. Okay, she won't be joining. Okay, thank you for informing, Shwana. So, electric field, this is a gradient of the potential. Okay, now you have this relation. Why is it important? Whenever I was saying that whenever you have the term gradient, gradient means that something is changing with respect to time, position. When we use the term rate means rate. Rate is always for time. See, rate is for time. You have a gradient for the position. So electric field as a gradient of potential means the change in potential with respect to the position. And why is there a negative sign here? Because this shows that electric field is in the direction wherever the potential decreases. Okay, wherever you see the potential is decreasing, it is becoming less. So there you will have the electric field. Now see, these are the partial derivations. More than this is important. See, if V is equal to KQ by X, what is the electric field? So just differentiate KQ by X. So when you differentiate this, okay, when you're differentiating this dV over dx, see, KQ here, when you have KQ, this will be taken out. So 1 by X will go to the numerator. It will become X to the power minus 1. And then you will subtract 1 as how to differentiate it. So in differentiation, we always put a negative 1, right? Minus 1 we always put. So this minus 1 is there in the power. That becomes X to the power minus 2, right? So differentiation and integration, that's why I've discussed with you. X to the power minus 1 goes up because this X is difficult to differentiate as it is. Power is minus 1. We put minus 1 here and we multiply a minus. That becomes X to the power minus 2. So we get the derivative equation E is equal to KQ by X square back. This is a very easy question. Quickly try this question, Shwana. Question 2. Right, Shwana. See, it will be minus x to the power 2. Very right, correct. It's just that when x is given, we'll put the value of x. So that becomes minus 36. So I think you've understood this concept well. Your answer was also right. Let's come to potential. One more thing, Shwana, when is your exam? Like right now, you don't have any exam, no? In between, directly boards are there, no? Or do you have something?
We have exams, ma'am.
Yeah,
We have exams.
you have exams. When?
Our pre-board is going on, and then we have practicals.
Pre-board is going on.
Yes.
Physics is done.
Yes, ma'am.
So how was the physics paper?
It was okay.
Can you share the question paper with me right now?
Okay, I'll see.
Yeah, please share that.
Ma'am, can I send you an email?
Yeah, sure. Why? What happened? On WhatsApp, it's not getting sent.
Actually, I don't have the phone in which the number is there.
Acha. Okay, Shwana, you can leave it. You can then send me later.
Okay, ma'am.
So coming to electric potential energy. Just a minute, Shwana. Just give me a minute. Okay, Shwana. You can send me the question paper later whenever you get the phone. So this is not, there is nothing urgency of it. Coming to potential
Okay.
energy. Okay. See, potential we discussed whenever the amount of work done that was required to bring a charge from infinity to a point. Okay. Now, when you have potential of a system, potential energy of a system is there. So what happens is that from infinity, you bring up the charges. Okay. Charges are there. You're bringing up all the charges. And at a particular point, you are putting those charges. Now, in the previous case, we just had the potential. Now, when the two charges are interacting with each other, interaction means, Shwana, means that they are able to exert forces on each other. Like if I say one charge is just existing, will it have any effect? No. It will just be having the potential. Will it be able to generate force? No. For generation of force, there is a requirement of another charge to be present. Without another charge, we'll not be able to generate energy because force will not be applied. So here, when you're talking about the potential energy of a system, you are bringing one more charge. So firstly, we are seeing when two charges are present. So look, potential due to the first charge when no other charge was present. Okay. See, this is the case. I have first brought the Q1 from infinity to A. Right now, Q2 is not there. So work done, what will be the work done? 0. Why? Because there is no other charge right now for Q1 to interact with. Do you get this?
Yes, ma'am.
And when I bring this Q2 back here, then these two charges are existing, which can create potential energy now because they can have the interaction with them. So first one's potential is 0 because it is just brought from infinity and there is no other charge to be present for the force to occur. Right, so that's why we're just having the simple 0, value 0. Now when another charge is brought up, this another charge will be interacting with the potential. So this becomes kq by r. So when you are calculating work done, potential has Q2 in it, KQ2 by R12, and you're multiplying it with another charge. So the formula of potential energy becomes K Q1 Q2 by R1 Q1 Q2 by R. This is the formula of potential energy. Similarly, if n number of charges are there, same procedure you will do. See, when first charge is there, nothing. When two charges are present, then two potential energies. When three are present, then this 4, then this 5, this like nth. So basically, you need to remember the formula of potential energy is K Q1 Q2 by R. This is a very simple question. Don't tell me rest of the things. Just tell me what's the value of potential energy. Shana?
Okay.
18 into 10 to the power 3. You've converted it properly. 18 minus 18 into 10 to the power 3. Negative charge is there, no, Shwana? Energy is scalar quantity. So you will not modify it by us. Okay. So if the charge is negative, you will also take the potential to be negative. Understood?
Yes, ma'am.
Okay. Coming to capacitance. Okay, see, so basically what is a capacitor? Capacitor is a device that stores the charge. Okay, the ability to store the charge is called capacitance. And the device that does this work is called a capacitor. So basically, it's the ratio of charge by potential. So you write this as Q by V, charge divided by potential. And the SI unit of it is farad. So you use it like 3 millifarads, 4 picofarads, like this. We often use for it. Now, capacitance of a conducting sphere. You know V is equal to KQ by R. And capacitance is Q by V. So when you take the ratio, you will be left with just R by K. And what is R by K? No, here you'll be left with, yeah. So K will be 1 over 4 pi epsilon naught. It will go up. So it will simply become 4 pi epsilon naught R. When you put in the value, considering Earth to be a sphere, see, 4 pi epsilon naught R is the formula. Okay, this is the formula for the sphere. But if I say Earth is acting as a sphere, okay, if I say Earth is acting as a sphere, so in that case, what can we say? The radius of the Earth we can put this as the value of rest of the things we know that those are constant, like 4 is constant, pi is constant, epsilon naught we know. Radius of Earth we put. So this capacitance, 711 microfarad, this becomes the capacitance of Earth. Just a minute. Okay, Shwana. So a 711 microfarad, this becomes the capacitance if Earth acted as a sphere of conduction, means if Earth was conducting. So you can use it for any device whose radius you know. Now, what's a capacitor? So basically, capacitor, I told you it's a device that is used to charge. So basically, two conditions are required. Two requirements are there to make a capacitor. You need two conductors, firstly, which have to be oppositely charged. And then there has to be a dielectric medium, which we say insulated medium between the charges. Then these conductors, they are used as a capacitor. They can be used as capacitors. So there are various types of capacitors: parallel plate, spherical plate, cylindrical plate. Okay, now, when we're talking about the principle of a capacitor, principle of capacitor basically means that you have to decrease the potential so much that the capacitance increases very much. Means, see, when we say the capacitance increases, okay, capacitance is inversely proportional to potential, right? If capacitance is inversely proportional to potential, if I decrease the potential a lot, so what do you think will happen to the capacitance? Will it increase or decrease?
Increase.
If potential is decreased, capacitance shall increase because it is inversely proportional to it. So what we do, we bring an uncharged conductor near our conductor, near our main conductor, we bring an uncharged. Why? Because the potential is zero. We earth it. When you do the process of earthing, the potential becomes zero. Okay, so this is why this is what is the principle of a capacitor. That capacitance of a conductor can be increased if you bring an uncharged earthed capacitor near it. Uncharged earthed capacitor means you are making its potential zero. Least potential means lots of capacitance. Is this clear to you? Yeah, Shwana, am I audible?
Now you're audible, ma'am.
Okay, okay. So, did you understand the principle of capacitors?
I was lagging a bit.
Okay, wait. Let me explain it again. See, Shwana, if the capacitance is inversely proportional to the potential and I decrease the potential, so will my capacitance increase or decrease?
Increase.
Increase. So Prince, basically we want larger capacitance because capacitance is of use to us. So what we do, we bring an uncharged, means without any charge, earthed conductor. Earthed conductor means you have connected it with the ground, and whenever the process of earthing is done, the potential becomes zero. So least potential, see this or our original conductor will be having some value of potential. But now, if this also has potential, the total potential would have been more. Now, what did I do? I have brought an uncharged earthed conductor near it. Now, what is happening due to it? The potential is decreasing, and it becomes zero because it is earthed. So, as a result of which, what happens? The capacitance increases much, and that is the principle, and that because what we wanted, we have achieved. So capacitance of a conductor can be increased by bringing an uncharged earthed conductor near it. Now got it?
Yes, ma'am. Thank you.
Okay. Now coming to the parallel plate capacitor, see, you just need to remember their formula. These derivations are there. I did it in the class, that's why this is written. But in your syllabus, it has been deleted. Let me just check once from your syllabus. Wait, then I'll discuss this. Wait. Okay, the energy stored in the capacitor is deleted. This is there. Energy stored in a capacitor. That formula only you need to remember. See, basically in parallel plate capacitors and all the derivations of parallel plate capacitors, you need just one. That is the formula of the potential gradient which we have seen. So potential gradient's formula was E is equal to dV over dr. That is potential divided by the distance. So see, two parallel plates are there. They have their electric field E. Now, in Gauss theorem, you must have studied that electric field is equal to sigma divided by 2 epsilon naught. So for one plate, you have sigma by 2 epsilon naught. For the second plate, it will be sigma by 2 epsilon naught. Now, when you add it, net electric field for both of these, it will become sigma by epsilon naught. That is the electric field. So what we do, the steps are the same. Calculate the net electric field calculate the potential using this formula, E into D. See, electric field is potential by distance. So when you put the electric field into distance, you get this QD by epsilon naught A. And then you have potential with you. You know the formula of capacitance as Q by V, you put it here. What are the steps? I'm repeating the steps because in all of these, the steps are the same. So the first step is you take the net electric field of the plates. Individual plates, you have to calculate their net electric field. Electric field is calculated, you calculate potential. Because for potential, you required electric field, calculate potential. Potential has been calculated, simply put in the formula of capacitance. So 3 steps, electric field, potential, capacitance. Okay, Shwana, this part is fine?
Yes, ma'am.
Okay, now see in all the parts, when the dielectric slab is filled with a dielectric medium, when the parallel plates are filled with dielectric medium in between. So always multiply it with a K. That is the dielectric constant. Just multiply it with a K. Now see, if there is a dielectric slab present, so this will be having some thickness T, total distance is T. Now, we have to find out for this. So here the electric field due to the dielectric slab will be different and the electric field due to the plates will be different. Due to the plates, it will be sigma by epsilon naught, what we have studied, the outside one. Due to the dielectric slab, it will be K times, so sigma by K epsilon naught. So when you go by the steps, when you calculate the net electric field, it will be this. Then you put it in the formula of potential. So for the dielectric, the thickness is T, so we multiply it with T. For the other one, the outside one, the thickness is D minus T. Distance between the plates minus the thickness of the capacitor. That gives the potential. So you have the potential and you then put it in the capacitance. So this is the formula. Again, if a conductor is there, whose electric field is there, is 0. Because electric field inside the conductor is 0. So again, the same steps will be followed. Electric field 0, this will be sigma by epsilon naught. And when you have the sigma by epsilon naught is left, the dielectric slab part is 0 because here it's a conductor. So this is the way you have to calculate net electric field, net potential, put it in capacitance, you get this. In short, you have the formula of all the plates like this. Epsilon naught A by D, K times epsilon naught A by D, epsilon naught A by D minus T plus T by K. C is equal to epsilon naught A by D minus T. So go through the derivations also. Energy, you just need to remember this formula. Half Q square by C, half CV square, half QV. So all these formulas are same, but it's just that there are different variations of each other because Q is equal to CV. Okay, so these formula you need to know, half Q square, whichever is given, you can apply that. Okay, in this question, Shuana, you just tell me, take time, read the question, and then tell me out of 1, 2, 3, 4, which is the appropriate formula. See, Shwana, the separation is more and the thickness of the plate is less. It means some space is left. So this is which case? This is the case when you insert a dielectric slab. That is option 3, like this. See, the separation between the plates is this and thickness is this. So it means some gap is left. So you use this formula. Understand? You have
Yes.
understood this, Shwana?
Yes, ma'am.
See, these formula, this will be used when nothing is placed. This will be used between the plates when completely a dielectric medium will be placed. If dielectric slab is partially filled, then you use this formula for fourth one. So this should be clear to you which formula you're using. And for spherical capacitors, again, you need to know the formula only. R1, R2 by 4 pi epsilon naught R2 minus R1. So how did we get this? Two concentric spheres are present. KQ by R1 will be the potential for the first. KQ by R2 will be the potential. That will give you the net potential. Take the ratio with the charge, that will give you the capacitance. Okay. These questions are like derivations which you can check. In sharing of capacitors, you can see when two capacitors are present and they are shared, means you have two spheres and suppose you have connected them with the help of wire or something. Now, the charges are unequal. The extra charge which is present will flow from one of the capacitors to the other one till the time both of them have the same potential. So in class 11th, you must have done thermal equilibrium when the charges flow till the time both the containers receive the heat flows till the time both the containers achieve the same temperature. So here also the potential till the charge will flow till the time the bodies will receive the same potential. So that potential which has now been reached is called the common potential. And this formula of loss of energy also, you just have to remember, derivation you need not do. It is C1 C2 V1 minus V2 whole square by 2 into C1 plus C2. Okay. So this formula, remember, C1 and C2, these are the capacitance and V is the potential. So it can be negative because that's the loss in the energy. Now see, whenever you have two plates that are separated by a distance and you have to see whether the plates are connected to a battery or not. So these cases come. So in those, just remember, this is the general case. Okay, this is the general case. So C is equal to epsilon naught A by D, charge is CV naught, potential is V, electric field is V naught by D. If the battery remains constant, then see what are the changes that occur. The capacitance gets multiplied to K. So it increases K times. What happens to the charge? The charge also gets multiplied with K and it increases. But what happens to potential and electric field? It remains the same. So see, if the question says the battery is left connected in the space between or with the parallel plate capacitor. So only capacitance and the charge will increase, the potential and electric field will remain the same. And if the battery is disconnected, then the capacitance will increase K times. Charge will remain constant here. The charge will be constant here. And potential and electric field, they decrease by K times because it will be divided by K. So they decrease K times. Okay. So this is it, which you need to remember from this chapter. And coming to series and parallel connection. So what is the division of charge? Charges are divided when the branching occurs. If the wire is just folded, if the wire is just turned, or if a device comes like capacitors are there in between, that doesn't hamper your charge distribution. Charge will flow as it is. It won't. If I say 4 coulomb is coming and I've just bent the wire, so it won't affect it. It will allow 4 coulomb to move through it. Likewise, if 10 coulomb is moving through a straight wire, let's say here 15 coulomb is moving, so even if the capacitor is there, it will allow the charges to move. So how does the charge divide then? Charges divide on branching only. When there is a branching, the charges divide. It can be equal, it can be unequal depending upon the voltage and rest of the factors. When you are dividing voltage, in case of voltage, see, when you are dividing voltage changes when there's a device like capacitor is there, voltage changes. See, here the voltage is VA, here the voltage is VB. So when you have put a capacitor, this changes from VA to VB. Again, when there's a resistor, this changes from VB to VC. So devices change. Branching does not affect your voltage. See, even if here it is V, it will be V only. Here it is V, here it is V. Bending of wire, the branching of wires, they do not affect the voltage. So devices affect, like see C1, C2, C3, they affect it. Okay. So see, in series and parallel combination, if capacitors are connected in series, how will you identify it? You will see the charges are the same. Charges that are flowing through it, they are exactly the same. So then this is how you identify a series. Equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3 up till nth. That will give you C equivalent. So you just have to use this formula and reciprocate the value to get C equivalent. Charge will be given by capacitance into voltage. These are the individual voltages. Divide the charge by the individual capacitance. This is how you can get it. And C energy is equal to half Q square by C or half CV square, depending upon what's given to you in the question. And coming to the parallel combination, you will see voltages are the same. V, voltage will be the same and the charges will be the different. So when you take the net charge here and you calculate the value of capacitance, you just have to add it. Just add it. For the net capacitance, just keep on adding. Two charges, it is 1 by C equivalent is given by 1 by C1 plus 1 by C2 plus 1 by C3 up till 1 by Cnth. And when you have C equivalent in series, sorry, in parallel, you just added C1 plus C2 plus C3 like this. So these are the things that you need to know in this chapter. Just go through the chapter. If you have any difficulty in any part, any portion, update me, let me know. I'll just discuss that with you. Which chapter do you want to revise, Shuana? Like after this? Any doubts in any chapter? Do you want to take any class for any chapter?
Chapter 4.
Chapter 4?
Yes.
Okay. Okay then. I think you have the document with you. Just discussion is left, na?
For chapter
Okay.
2, ma'am.
Only chapter 2 you have.
No, I didn't understand what you just said.
No, this one note, the notes of chapter 4 are with you?
No, ma'am.
Okay. What's your mail ID, Shwana? Can you just type it in the chat column?
Okay, ma'am.
It's already shared with you, Shwana. Acha, you share. I'll share it again.
It's the CMA Jazz one, ma'am.